So welcome everyone to today's webinar. I'm Madhu Govindarajan and I work in technical marketing at the MathWorks. I focus on hardware connectivity with our software, and today we will see how MATLAB and Simulink can help you program your Raspberry Pi boards. Before we get into the agenda for today, let's take a quick look at the demo in action. So this is a security system that I built that sends out a tweet every time when someone is at my door. What this algorithm does is it monitors my door, and every time when someone is there, it lights up an LED and sends out a tweet. This could come in really handy because all I have to do is follow the Twitter robot, and every time when someone is at my door, I will know no matter where I am. First, we will start off with a quick overview of MATLAB and Simulink. Then, I will show you a product demonstration on how MATLAB and Simulink helped me build this project. In the end, we will see some key takeaways from this webinar. For those who are not familiar with MATLAB, it is a programming language and an interactive development environment. It is used for developing algorithms, visualizing and analyzing data, and performing numerical computations. You can import data into MATLAB from files, other applications, or external devices. Once the data is in MATLAB, you can explore and analyze it through built-in functions and visualizations. Commands can be executed one at a time, providing immediate results. This allows you to explore multiple approaches and iterate to an optimal solution. You can create scripts and functions that allows you to automate and reuse your work. Add-on toolboxes extend the MATLAB environment to solve problems in a range of applications, including communications, signal processing, video and image processing, control design, and even computational biology. Now let's talk about Simulink. Simulink is a block diagram environment with libraries that is used to model and simulate complex systems. Let's take the example of a smart wind turbine that adapts to wind conditions to optimize power generation. In Simulink, you analyze and understand such complex systems by simulating the block diagram. You get your model to simulate by simply pressing the play button. You can configure your model to have just the right amount of detail for your specific task. For instance, you can start with an ideal component to determine all the requirements, and then you can switch to a finer model to design your embedded software. From the model, you can generate code to prototype and test in real time and deploy it onto your embedded system. Till now, we saw how MATLAB and Simulink are used in a very generic sense. If your focus is on hardware projects alone, MATLAB helps you read, write, and analyze data interactively while being connected to the computer. Simulink, on the other hand, helps you deploy your algorithms so that they can run independent of your PC and on the hardware board itself. I purposely chose two different hardware schematics to emphasize on the point that you can use the same approach to program different hardware boards. So in the product demonstration section, we will cover these items. First, we will see how to set up the Pi so that we can read and write data from MATLAB wirelessly. Then I will show how I developed the image processing algorithm using MATLAB. After this, we will see how I deployed the algorithm to the Raspberry Pi using Simulink. For the first section, I've listed all the steps involved. We will establish a wired connection and show how to use that connection to set up the Wi-Fi on your Pi. So let's go to MATLAB and see this in action. So this is the default layout of MATLAB. We have the current folder on the left-hand side where you can see all the files and folders, and you can also navigate between folders using this. This is the MATLAB command window where you can declare variables and execute any of MATLAB's functions and see immediate results. The workspace shows all the variables that were created from MATLAB command window, and it also provides you some quick information about these variables. So I've created this text file that details all the steps that you will have to go through to set up your Pi, and I will share this at the end of this webinar. To communicate with any hardware from MATLAB, the first step will be to install the respective hardware support package. For this, you can go to Add-ons and click on Get Hardware Support Package. Here, it allows you to install the support package of your choice from the internet. So after selecting the right support package, you can follow the process using the next button and enter the MathWorks credentials when asked. So if you don't have a MathWorks account, you can create one from this installer itself. After you've installed the Raspberry Pi support package, it shows you steps to automatically update the firmware on your microSD card. This is a necessary step in the installation process. I've already done this on my computer. Let's see how I can test the wired connection to the Pi using Raspi function. So this function creates an object on the MATLAB workspace called myPi, which represents the connection between the Raspberry Pi and MATLAB itself. To understand the different functions that I can use with this Pi, I can use the methods function on the variable that I just created on MATLAB command window. For step 2, we need to open a shell from MATLAB. For this, we can use the open shell function on the myPi variable that we just created. This is basically the terminal window that you will see on the Raspberry Pi. And you can edit the SSHD configuration files from inside this terminal window. And you can see that I have added the necessary information onto the configuration file. So similarly, I edited the WPA configuration file to add my network information like the SSID and password. After this, you will have to remove the wired connection that you have to your Pi and restart it. Remember, when your Pi restarts, it is going to connect to the internet using the Wi-Fi network and it will get its own IP address. So now, to communicate wirelessly for the first time from your MATLAB to the Pi, you will have to enter the IP address, username, and password. After the first time though, I can use the Raspi function without any inputs arguments to establish the communication wirelessly. Now let me bring up the methods available for the Raspberry Pi object. You can go ahead and try all the functions available in this set. To know the syntax for a specific function, all you have to do is search the documentation by typing doc and the function name in MATLAB command window. In the documentation, we can see the syntax and understand what the function actually does. Now let us go back to the slides. We saw how to establish wired communication between MATLAB and the Raspberry Pi. We then saw how to set up the Wi-Fi using this wired communication to establish wireless communication and read and write data from MATLAB. In the next section of webinar, we will see how I developed the security system algorithm using image processing toolbox and MATLAB. The desired security algorithm should be able to take the reference picture and current picture and tell me where the difference exists. This way, we can visually confirm that the algorithm works as intended, and then I can deploy it to the hardware in the next step. Now let's go back to MATLAB. So I've created a script called security system algorithm in MATLAB. Scripts are a group of MATLAB commands that achieve a collective purpose, and in this case, it will be my security system algorithm. So this is the traditional editor, and you can see how MATLAB is suggesting me to open it as a live script. This is a new feature. When you convert your traditional scripts to live script, you can see that the existing markups got converted to formatted text. The cool feature about live scripts is that it allows you to see the results along with the code that produced it in a single environment. In the traditional scripts, the code is on the editor and the results would populate on the command window. You can choose to show the results either on the right side or inline. If you display the output on the right, you can click on the block of output to know which line of code was responsible for this. So in the first step, I am collecting two snapshots from the camera. And we can see that they look identically the same. I am going to compare these two images mathematically. So images are three-dimensional matrices, as you can see here on the workspace. To subtract two images, I'm converting them to a 2D matrix or a grayscale image. We cannot see the minute differences in this image, so I've displayed the maximum difference value right here. We can see that it is definitely not all 0, which means that the image is not completely black. So to understand more about the difference, I'm converting it to a black and white image. The other reason I'm converting this to a black and white image is that it is easier for the computer to understand because a black and white image consists only of zeros or ones. We can see that by looking at the variable type, which is logical. In the next step, I'm comparing the changed pixels to the original image itself and see if it is greater than 5%. The algorithm thinks that there is someone at the door because of all the noise. So to eliminate this, I'm going to threshold the images to drop any minor differences in the black and white image that we got. Now we can see that the noise is almost completely eliminated, and the algorithm says that there is no change in the frame as expected. So this algorithm can be further improved because right now it is monitoring the whole office, and I would like to ignore anyone who's on the glass window. I'm using MATLAB's interactive way to focus on specific portions of images, the IMRect function. So now the boundaries of this section are available in the position vector. So to test this algorithm, I've created another script called testing SS algorithm, and what this script does is it collects the new image, compares it with the reference. It then thresholds the image and focuses on the door portion. So let's put this to a test. We can see that when I'm standing at the window, the algorithm will not detect any false positives. However, when someone is actually at the region of interest, my door, it would recognize that someone is at my door. The other useful functionality of Live Script is that it allows you to add equations, hyperlinks, and images as well. So this way, one can create an interactive narrative that you can share with others in the format of PDF or HTML. Notice how the PDF generated has all the results that we observed along with the code that produced it. So now all I will have to do is create two PDFs, one with the person on the window and other with the person at the door, and share it with my colleagues to show that the algorithm is working as intended. Now let's go back to the slides. So the next step would be to deploy the algorithm that we just created using Simulink. As I previously mentioned, Simulink is a block diagram environment. To bring in textual code, one of the easiest ways is to use MATLAB function blocks, which can reuse any algorithm that you have already tested in MATLAB. I'm going to use this model to give you a quick demonstration of Simulink and my security system algorithm. So to understand Simulink models, remember two key items. Read them from left to right, and remember that this is a time-based programming environment. So let us see what I mean by that. So this block captures images from Raspberry Pi camera board or other USB camera once every 2 seconds and outputs RGB values as individual vectors. So I'm combining these values to get a 3D matrix of the image. I will then pass this to the MATLAB function block. Here I'm using the same code that we saw, and I'm saving the first instance of the image as the reference image here. And since we want to deploy this code, I've removed all the display items and I'm setting a flag and a message. So the message will be sent to ThinkSpeak channel, which we will see in a little bit, using this write API key. The flag is then used to turn on or off the LED that is connected to the GPIO pin 23. In this explanation, I did not talk about enable block and scope block. We will see the scope block in action in a few seconds. But let's talk about the enable block. So what this block does is it makes this an enabled subsystem. A subsystem is a collection of blocks that achieves a single purpose, very similar to scripts that we just saw. So we can choose when to run this security system algorithm and when to disable this, all thanks to the enable subsystem. So the main reason I chose to go with enable subsystem is that I don't want the Pi to be running the security system algorithm when I'm in my office. So to choose when I want to run the algorithm, I'm using a push button. This block reads the GPIO pin number 18 once every half second, which is then fed to the state flow chart. So this is another way to bring textual code into Simulink. The state flow chart is exactly like a toggle switch and toggles the output every time I push the button. This way, when I want to start the algorithm, I push the button and the state flow chart starts outputting 1. When I push the button again, the state flow chart starts outputting 0, which will disable the subsystem. We saw the demo in action at the start of this webinar. For that, all I did was use this deploy to hardware button to send the entire algorithm to the Pi. This mode programs the Pi so that it can work independent of the PC. Another feature in Simulink is called external mode, which allows you to monitor signals and tune parameters while the code is still running on the Raspberry Pi. So let's see this in action. Once I press the play button, what Simulink does is it generates the code equivalent of this model and sends it to the Raspberry Pi wirelessly. So this feature will be really helpful to see how your algorithm is performing before you deploy it to the hardware. So I can see from this scope that every time I push the button, it toggles the output here, thereby enabling or disabling the entire set of code in the subsystem. Now let me talk a little bit more about ThingSpeak and show how sending this message corresponds to sending a tweet. ThingSpeak is a free online data aggregation tool that is available on the cloud. It is typically used to collect data from the sensors, which would be the things in ThingSpeak, and provides instant visualizations for the data. It is popular among people who are experimenting with IoT. We will now see how the ACT portion of ThingSpeak helped me in the context of this demo. So you can create a new channel and fill out all the necessary details about the channel, title, description, and field. Instead of creating a new channel now, let's go take a look at the one that I've already created. So to get the right API key that I showed in the Simulink model, you will have to go to this section under your channel. The app section of ThingSpeak shows all the analytics and actions that ThingSpeak can do for you. To be able to send out tweets, you will have to link your Twitter account from the ThinkTweet section on this webpage. Once you've done that, you can create a React going to the React section and clicking on New React. Here you can see how I'm using the field from a specific channel using this syntax. So this ensures that every time there is a change in the value, it sends out a tweet. Now let's go and see some of the key takeaways from this webinar. We saw how to incorporate image processing routines into your hardware projects and how to validate them using MATLAB. We also saw how you can deploy your algorithms to your hardware using Simulink. Although I did not show in this webinar how you can program your hardware using the same approach, if you're interested, you can go to the link on the screen or search how to use MATLAB with Arduino boards on E14 community. This will bring up a recent webinar that we have done with E14. Similarly, there is a build your own temperature display manual on E14 that shows how MATLAB can help program BeagleBone Black. For LEGO EV3, you can go to YouTube or mathworks.com and search for obstacle avoidance using LEGO EV3. And this video explains this project in detail and shows you how to program LEGO using Simulink. So hopefully the demo that we showed today will inspire you to come up with interesting ideas on how to improve the security system that I had. I will share my MATLAB and Simulink files on E14, and you can post your videos of the improved version on E14 community.